Okay, we are back one more time for one final lecture on historical astronomy. All right, so we have gone through 5 of the 6 historical astronomers that we're going to go over. This last lecture is about Newton. The last lecture we did was about Galileo and his transformative observations and free fall experiments. And this lecture is about Isaac Newton, the laws of motion and gravity that he developed and how they translate into planetary orbits. I want to remind you that for your paper this semester, you are not allowed to use any of these 6 historical astronomers. All of these are off limits, but I promise you there are many, many more to choose from that have made similarly groundbreaking contributions to the field. Okay, so Galileo never quite figured out why objects go through free fall and why free fall for all objects is the same. However, here comes Isaac Newton, who's actually born the same year that Galileo died, incidentally. Galileo died on January 8th, 1642, and Isaac Newton was born on December 25th, 1642. So a nice little synergy there. So Newton did a lot of work significant to astronomy. He worked a lot with light and optical systems. He developed the first reflecting telescope, which are actually my favorite types of telescopes to use. And it's different from what Galileo used. But for our purposes here, and probably what he's most well known for today, is how he associated force with acceleration. All right, so a force is a push or pull on an object. It can either be direct, as in like we are directly, pushing a box, or it can be through a field, like a magnetic field or a gravitational field. Acceleration is a change in speed, right? Either speed up or slow down, or since velocity is a vector, that is, it encompasses both a speed and a direction, you can also accelerate by changing direction. Like if you're going around in a circle at a constant speed, you are still accelerating because you're constantly changing direction to kind of stay in that circle. So this B right here, he could be going the same speed, but he's constantly changing directions, so he's accelerating. So this kind of explains free fall, right? Acceleration happens because there is a force acting on it. Newton elaborates on this connection between force and acceleration in his 3 laws of motion and his law of gravitation. So let's start with the first of Newton's laws. It is colloquially known as, objects in motion tend to stay in motion, but it's a little bit more nuanced than that. So what Newton actually said is that objects in motion with a constant velocity will stay in motion unless a force acts on it. So remember, constant velocity means straight line motion, no acceleration. Newton's first law is otherwise called, the law of inertia. So inertia is basically how hard it is to change an object's motion, right? It relates to mass. The heavier an object, the harder it is to stop or speed up or change direction. And this is an intrinsic property of matter. So to change the motion of an object with constant velocity, we need a force. So this is Newton's first law, this law of inertia. I include down here a Calvin and Hobbes cartoon. He's asked to explain Newton's first law in his own words. He makes up a bunch of words and thinks he's going to get away with it. You would not get away with something like that in this class, just for reference. Okay, so Newton's second law is actually usually referred to in the form of an equation, right? F equals ma. Force equals the mass of an object multiplied by its acceleration. So it might be better understood written in a slightly different way, though, rearranged. The acceleration is equal to the force applied to the object divided by the object's mass. So acceleration is related to the force applied and the mass of the object. The more massive the object, the larger force you need to apply to get a large acceleration. So what we're talking about here is something extrinsic to the object, like something needs to act on that object. Newton's third law is probably the most misunderstood of the three, um, for a good reason. It's not an intuitive law. It's commonly said like this: for every action, there is an equal and opposite reaction. So what on earth does this even mean? So when two objects interact, the force they exert on each other will be the same. So this seems really counterintuitive. Maybe think of it this way. So what we see kind of in daily life when like something big really knocks over something small is that isn't the force necessarily, it's the acceleration. So think about the equation in Newton's second law, right? F equals ma. If we have a really big thing, the acceleration we would see is the force divided by a very large mass. Now let's say that a really big thing interacts with a small thing. The acceleration we would see is the force divided by a very small mass. The force between them is the same, uh, but their mass affects how easy it is to change their motion. So I know it's kind of hard to wrap our mind around. We can check this out, this simple diagram. So if we just want to lean against a wall, for example, um, that wall is likely much heavier than us, much more massive. Um, but there's no movement really there. And that's because just the force that we are putting onto the wall is being kind of given back to us by the force the wall places on us leaning against it. Like I said, it's not intuitive. It's hard to wrap your mind around. It might become a little more clear if we think about how you interact with the Earth, right? The planet we're on right now, which we'll get to in a slide or two. So another question that Galileo grappled with is, why should things orbit other things? Like, why should this even happen? He never quite figured that out, but Newton did when he developed his law of universal gravitation. Basically, any object with mass will attract other objects through a gravitational field. So the gravitational force exerted depends on the mass of the two objects and the distance between them. So the Newtonian equation for the gravitational force is here. You have the mass of one object times the mass of a second object divided by the square of the distance between them. Okay, this is very important that we know that it's an inverse relationship, right? We divide by the distance. This G here is called the gravitational constant. It's a proportionality constant. It wasn't determined by Newton, but it is important to the equation today. Okay, so the story here is that Newton was sitting under a tree, kind of looking up at the moon, contemplating why the moon should orbit the Earth when an apple falls from the tree. And this is supposedly Newton's like aha moment. So Newton's third law would imply that the force exerted by the Earth on the apple and the force exerted by the apple on the Earth is the same. but we only see the apple fall to Earth, not the Earth fall to the apple. But that's what's happening. But remember, what we see really is acceleration, right? So the force can be the same, but that force results in a much uh, larger acceleration for the apple compared to any sort of upward acceleration from the Earth, right? Force is the same, but the acceleration is going to be much more for the apple, so we see it fall towards the Earth. Okay, so this phenomenon is more obviously demonstrated if we look at the Earth and the Moon. So the Moon is pulling on the Earth, and the Earth is pulling back on the Moon in the same amount. So the orbit itself is a free fall. And unlike Earth and the apple, we see the effects of the pull of the Moon on the Earth through high and low tides. So we get these high tides when the moon is just overhead. It causes a bulge in the oceans on both sides of the planet, and there are 2 high tides per day and 2 low tides. And so this is kind of how it works. So you have the moon, the high tide kind of happens almost right under the moon on both sides of the planet, and the Earth kind of rotates underneath it. So we kind of go through high tide and go through low tide. But this is because of the gravitational pull of the moon on the Earth. The sun also tugs on the Earth when the alignment is just right, like the Earth, the moon, and the sun are in a row. So this can either be Earth, a new moon, and the sun, or it could be a full moon, the Earth, and the sun. There's an additional pull that causes especially high tides and especially low tides. So these are called spring tides, and they occur, as I mentioned, during the new moon and full moon phases. There's also times when the sun causes much lower high tides, and that's when the orientation is kind of more like an L shape. So we have a quarter moon here, the Earth and the sun, or a third quarter moon here and the sun. So kind of L shapes in one of these directions. So this causes tides to be lower. And this kind of makes sense. You've got the sun kind of pulling in a different direction than the moon is pulling. These are called neap tides, and they occur during the first and third quarter phase. So here's an exaggerated animation of how we get spring and neap tides. So this animation shows how much of the tide is due to the sun and how much is due to the moon, right? So we have this orange circle here. This is a solar tide. The blue circle is the lunar tide. And then we have this kind of a tealish area that's the actual resulting tide. So the moon has a much bigger effect on the tides than the sun. So why might that be? So the gravitational force, remember, is proportional to the masses of the two objects and the inverse of the square of the distance between them. So, right, it's an inverse square relation. So even though the sun is much larger than the moon, it's also much further away. So in this case, the moon's effect on the tides, even though the moon is so much smaller, it's actually much stronger than the sun's. And hopefully you can see here how the actual tides change as the moon goes around the Earth. You can see the sun's effect on these tides. Okay, so things with mass exert a gravitational force. But what does this actually have to do with the orbit, like the closed orbits that we see for the moon and the planets? Why do closed orbits happen? So let's use the moon and the Earth as an example. The gravity of Earth pulls the moon towards the Earth. So if Earth here, its pull of gravity wants to pull the moon in close. But the moon also has a velocity and a momentum kind of in this forward direction. So Earth wants the moon to come to the center, but the moon wants to keep going in this direction here. And so the result, if we can get these two things to balance, is an orbit that looks something like this green circle here. And the balance of these two kind of keep the moon in this orbit. So Newton did a thought experiment that kind of demonstrates this, and the schematic of it is kind of right here, called Newton's cannon. So let's say a cannon was put on a very high mountain. Now let's say we launch a cannonball parallel to the ground. If the cannonball doesn't have enough speed, it's just going to fall to the ground. So right here, these red lines here, it doesn't have enough speed, it falls to the ground. As we give it more and more speed, more velocity, the ball will go further and further until actually it has enough to actually enter orbit and go all the way around the Earth. However, if we give it too much speed, the ball will escape the Earth entirely, will escape the pull of the gravity. So over here, this is a table of how quickly an object needs to be traveling to actually orbit the Earth. So under about 8 kilometers per second, the ellipticity of the orbit is less than 0, so it's negative, and the result will be the object crashing down to Earth, so these red lines here. If the speed is exactly 8 kilometers per second, the ellipticity is 0, which is actually a perfectly circular orbit. If the speed is between 8 and 11 kilometers per second, the ellipticity is between 0 and 1, which is an elliptical orbit, right? That's what most of orbits are. If the object is moving at more than 11 kilometers per second, the ellipticity ends up being greater than 1, which means the object will eventually escape. It's this blue line right here. So under 8 kilometers per second and over 11, the under 8 will eventually crash. The over 11 will eventually escape. As part of your homework, you'll get a chance to play with some simulations of objects traveling at various speeds and answer some questions based on that. If you have any questions about how to interpret these simulations, please shoot me an email or come by my office during office hours.